So today I'm going to cover, at least I'm going to try to cover 3 topics. And I'll finally get to the IP header. I've been meaning to talk to you about this for a while now. And so we'll go into the IP header and I'll talk about address allocation. How do we get the addresses to the hosts and routers in the first place? And then once we have an idea how to get addresses, we'll talk about routing in a local area network, which we also call a LAN. So those are the 3 things. As I mentioned in Piazza, this is sort of after the the midterm is going to cover up to the IP header. So that's when you can turn your brain off, and then for the final, we'll start address allocation. No, I'm just kidding. Okay, so IP is the protocol that holds the internet together. Okay, everybody or every device, every router, every host has to agree on one thing, which is IP. And the reason they have to do that is because the addresses that are in the IP header decide where it's going to go to. So if people don't agree on it, then you can't get from here to there. I mean, so everybody has to agree that this is the IP address. Now, it's not exactly true. Strictly speaking, you can take the IP address, sort of translate it to something else internally, and then get back to an IP address inside some private network. And in fact, that's done inside the backbone. But everybody along the path has to agree that if you translate it from IP to something else, you've got to get back to where you started from. Otherwise, it's not going to work. Okay. So the IP header is the set of information that's carried on the front of every IP packet. So you call that the IP metadata. So you have the data which you're actually sending, and then this is like the envelope for a letter which carries the address and the stamp, source address, things like that. So in the same way, the IP has a header. And when you try to understand any new protocol, it's often easiest to understand the protocol by looking at the header. So you look at the header, and you look at all the fields in it, and that tells you what the protocol does. It's like an X-ray into a protocol. So you can, if you can get the protocol headers and look at them, you pretty much know what's possible. So for example, if the IP header didn't have some field is missing, then you know you can't do it, because if it's not in the IP header, it's not going to get done, right? So we have some good way of doing it. So it's worthwhile looking at all the fields. Now, typically, when we describe the IP header, we are going to put so many bits for each field and so on in the layout. It actually doesn't really matter. What's really the only thing that matters is what the fields are. So I'm just going to write them down. We will start with the first one. So this is a field. The version field tells you what version of IP is being used. And at this point, there are only 2 versions, 4 and 6. So sort of a brief sort of digression into why we need version numbers. The reason for version numbers is because things change, right? So we want to design a protocol that's going to last 10 years, 20 years, or IP has been around for about 40 years now, right? It'll be 40 years next year, so it's 39 years old. When you design such a protocol, you want to make sure that it's going to last for a long time, right? So if you're working somewhere, you design a protocol at the application layer, for example, your tic-tac-toe protocol. Okay, you might come up with a protocol, and then you might decide that it's going to last 100 years. How do you know what people are going to do 100 years from now, right? So what you do is you don't know. So you put a version number on it, and what you do is you put the version number, let's say 4 or 3 or 2, whatever, and then if you change the protocol, you change the version number, the receiver then says, okay, if this version is the old one, then I can go do the old processing. If it's a new one, I'll do the new processing. And this allows you to be backwards compatible, right? So whenever you have a protocol, it's good to be backwards compatible, because there will always be people who don't upgrade, right? The people who continue to have the old version, and then to support them, it's always good to have version numbers. So it takes a few extra bits. So every single packet on the internet carries these 4 extra bits, which is sort of a lot of wasted capacity, one might say. On the other hand, it allows evolution. Okay. So IPv4 came out, so in 1973. I don't even remember whether there was 1, 2, and 3. I think they went from straight to 4. Probably not. Maybe they had some 1, 2, and 3, but I have no idea what they were. I've never seen them being described anywhere. And then 5 was a version that didn't quite make it, so they went to 6. And 6 has been the protocol of the future for the last 20 years. It's always been the protocol of the future. Okay, so there's a joke about Alice in Wonderland. And Alice, she goes to the Mad Hatter's tea party, and the Mad Hatter is pouring her tea, and he said, "You should have come yesterday. We had jam yesterday." And she said, really, jam yesterday? He said, yeah, and jam tomorrow. And jam yesterday, jam tomorrow, but no jam today. She said, what if you came tomorrow? She said, well, tomorrow there'll be jam yesterday and jam tomorrow, but no jam today. So it's IPv6 is like that, you know. IPv6 tomorrow, but not today. So every day it's next day. It was supposed to have been rolled out, and every year there's a big initiative, we're going to roll it out. Right now it constitutes about 0.01% of all traffic on the internet, and chances are it'll go up to maybe 1% in the next, who knows, 10 years, something like that. So, and as we go into routing a little bit later, you'll see why IPv6 is so difficult to get into it, to change to, because everything has got to change. Every single router has got to change. Every single host has got to change. All of DNS has got to change. And all the embedded applications which have hard-coded IP addresses in them, which are IPv4 addresses, have also got to change. So for the indefinite future, we're going to have v4 and v6. And so for now, we're just going to focus on v4, v6, again, it's for the future. So that's, and the main difference between v4 and v6 is just that v6 has longer addresses. v4 has 32-bit addresses, and v6 is 128-bit addresses, so it's 4 times longer, and that's the main difference. The other differences are really minor. It's really more addresses. Okay, so that's the first field. The second one is the header length. Okay, and this is in words, which is 4 byte, which is 4 bytes. So why do we need the header length? Okay, why would anybody need a header length field? Does anybody have any idea? Anyone? Yeah. Yes.
Because it's all zeros and ones, right? So don't you need to know when
Well, it's all zeros and ones, true, but let's say you knew that the header was always going to be 20 bytes. Then you don't need a length field because you count off 20 times 8, 160 bits, and that's your header, right? So why would you need a header length? Yes, Clarence?
There's a limit to the information that can be held in the header.
No, even if it's a limit, that doesn't require a header length field. The length field indicates something of yes.
So that you know, like if you have like some sort of malformed packet.
No, malformed packet is just going to have zeros corrected to ones or ones to zeros, right? The length isn't going to help you, right? Anybody else? Yes.
Is it kind of the same thing? It allows you to expand in the future.
Expand in the future, yeah, but you know that from the version number, right? So let's say version 6 is 25 bytes long, for sake of argument, right? Then yeah, it's version 6, 25, a count of 25 bytes. Otherwise, I don't, a count of 20 bytes. Anybody else? Why do you need a length field anyway? I mean, if you know what the version number is, you don't need a length field. Any guesses? Well, there's got to be some reason for it. So why do you put a length field in anything? Why, what is the length? Yes?
So you know how long it is.
How long it is. But why do you need to know how long it is?
If the length varies.
That's right. Why would the length vary?
Different purposes.
That's right. Okay. So the reason is correct. The reason is because the header length can vary, right? And the reason it can vary is because another field is called the options field. And the options are optional, right? That's the meaning. So the header length, typically the header is 20 bytes, which is 5 words. And like almost all IP packets are 5 words. Almost all IP packets have a header that's 5 words in length. However, it is possible to add options to the IP header. And if you have those options, then the length field increases. So what kind of options could you have? One option in IP is to say, it's called the record route option. It says, okay, as I go through, each router is supposed to add to the header what its IP address is, right? So you can kind of, just like you do trace route, you can, as you have a path, each router will add the router address over here, and then it will actually compute so if you do ping, I think this is ping minus capital R, that's a record route option. That sets a record route option on the IP header. What will happen is you'll actually get back the path from the IP header. However, this is not implemented everywhere, and some routers, in order to increase the speed of the router, whenever they see the header length is not 20, they'll just silently drop the packet. They'll just say, yeah, it's too complicated, I don't want to do it. They'll just drop it, okay? And IP is best effort, right? It's not guaranteed. So, you know, their best effort was to not make any effort. And they'll say, you know, either they ignore it or they drop it, one of the two. And so there are some other options. The most commonly used one, as I said, is the record route option. But again, the designers, back in 1973, figured out that we don't know what the future is going to hold. You know, we know that we hope that the internet is going to be successful. Remember, the internet was a lab experiment that went awfully right. Okay, it was what they call a success disaster, because it wasn't completely figured out, and suddenly everybody was using it, and it became completely out of control. It's like you're growing a bacterial culture in your lab, you know, and suddenly it explodes and takes over the whole world, and it wasn't quite properly engineered. Okay? And as you'll see later, when you talk about security, the internet is a lab experiment gone wrong, okay? And it's an awful, awful disaster. Okay? But at any rate, that will come later in the story. They were smart enough to put in the option field because they thought maybe someday somebody may want some options, so let's allow that. So they put in the header length field and the option field. And it was basically an experiment, right? So they said, we don't know what's going to happen. Even we don't know what we want, you know, 5 years from now. So let's put it in, and we might want to use it later. So that's the option field. And that's why you have the header length. And if you didn't have options, we wouldn't need a header length. The fourth field is a very sad field. It's called the type of service field. And behind this innocuous-looking term is a very, very important and tragic story of many people's lives, including mine. Okay, so what's going on here? How can there be a story behind a field? The type of service is trying to tell the network what service this packet wants, right? So let's think about what that means for a moment. So let's say I have a voice call, a Skype call that's going across the internet, and I have somebody else transferring, you know, a BitTorrent file, you know, a very large file. Okay, so just think about this. Here's a router, and the router gets one packet that's a voice packet, and then there's another packet that's a BitTorrent packet, very large packet. The voice packets are typically quite small, about 40 bytes, 50 bytes, really small. And here's this very large packet, and it's a lot of very large packets actually, which are all the BitTorrent packets. It's a couple of gigabytes, right, per file. So you got all these big packets sitting here, voice is sitting over here. Now imagine that you go to a place where there's a queue. So I used to say go to the bank, but of course you guys go to ATMs. So I don't know, the Tim Hortons, right? So you go to Tim Hortons, there's some guy ahead of you who wants to buy, you know, 20 double-doubles and, you know, big box of donuts. You want to select every one of them. And there's not one of them, there's 15 of those guys. And you just want one small regular coffee and you zip out of there, right? So they're all standing in line ahead of you. Okay, that's what it looks like to the small voice packet. Voice packet is sitting there, and these guys selecting all their, using up all the resources of the server ahead of them. What the type of service field said was, you know what, why don't we let this guy zip ahead, the voice packet zip ahead, cut ahead of everybody else in the queue, and this way they won't suffer long delays. And if they don't suffer long delays, you know what, the big packets won't even notice, because anyway they're getting a BitTorrent, right? It's going to take 4, 5, 8 hours to get the movie they're illegally downloading in the first place. So you may as well let the voice go through. Even in your own home gateway, you might argue that it makes sense to have, you know, if you're doing a BitTorrent and a Skype at the same time, that your Skype packets should go ahead of your BitTorrent packets. Kind of makes sense. That thinking of delay sensitive and delay insensitive traffic went into the putting in the type of service field in the header. So okay, we'll have the type of service be delay insensitive. We don't really care, you know, as long as we get through someday, it's fine, doesn't matter. You know? And the other one says delay sensitive. I really care about delay. Now push me through the head of the line. Exactly same situation holds in the road traffic, where we have ambulances and regular traffic, right? Ambulances zip through to the front, right? There's a red light, doesn't matter. They turn on the siren and off they go. We want to have sort of the ambulance type of service, and we want the you know, semi 18-wheeler truck type of service, so just go through. Delay is not so important. To get this to work, however, requires everybody in the internet to collaborate. Everybody has to agree to it. So they can agree on IP addresses, that's fine, but they also have to agree that if the ambulance bit is set, everybody is going to give it priority. But, and here's where the big problem of the internet is today and will remain forever, as far as I can make out, but why should everybody not set the ambulance bit on all their packets, right? It's like saying, I can go first class if I just set my ambulance bit. It can go first class. Why should everybody not set their bits to be first class? If first class doesn't cost anymore, everybody will fly first class, right? So if ambulance bit doesn't cost you anymore, everybody would turn the ambulance bit on. So we'd say, yeah, I'm an ambulance too. Let me through. So you immediately see that to have any kind of type of service, you got to have teeth. You got to say, okay, no, you must enforce the rule that yes, you can or cannot turn this bit on. If you have that bit on, you better be an ambulance. Otherwise, you're going to send you to jail. So if you get a flashing red light and you put it on your car and you go through a red light, you can go to jail, right? But we don't have a police on the internet. If your packets are going to, let's pick a random place, Sierra Leone, the Sierra Leone ISP is not, I'm assuming nobody here is from Sierra Leone. I'm sorry if I offend anybody. But that particular part of the internet has no way to enforce that you do not set this bit. And the other way around. If they set bits, if all packets emanating from Sierra Leone happen to have the bits set, there's nothing you can do about it. They're their own independent country. And if they insist on putting all the bits to one, either you ignore all the bits or you kind of just, you don't know, right? And the internet is designed in a way where the endpoints are sort of anonymous. You don't really know who's doing what, where, when, where the bits are coming from. And so the type of service bit, on the other hand, is something where there's uniform behavior. Everybody's got to agree to it. Everybody's got to believe in it. And importantly, you have to actually charge for it. Otherwise, there's no repercussion to it. And to charge for it means that if I send a packet to Baidu.com from here, some of that transit is going through China, right? Because it's in China. We know that. It's in Beijing. So from the moment it enters China to the time it gets to Baidu, certainly it's with some Chinese ISP. And if they're going to give higher priority to my packets, they want me to pay for it. So what am I going to charge them for? So I do a Baidu search from here. I'm going to pay them 1/10,000,000th of a penny for that search. And I'm going to do that for every search. I don't even know. I mean, if I go on a website and there are 20 different ads, who am I going to pay and for what? And how much? And how's it all going to be added up? So the accounting infrastructure to account for it is basically impossibly complicated, and so never got done. And because it never got done, we don't have it. And so this type of service field, which went into the design of the internet at that time, is basically ignored. It's just for 3 bits sitting there. Nobody's using them. And people use them for other purposes because it's unused. So where is the sad story here? The sad story here, and I'll tell you that in just 1 minute, starting now, is that around 1989, people in the phone network, in the phone industry said, we know how to do type of service. We know how to do that on the phone. Why don't we make the internet look like the phone service and provide good quality of service? And they said, well, IP is terrible. It's not very good. We're going to do it a different way. We're going to do it using a technique called ATM, asynchronous transfer mode. And without going into too many details, it's virtual circuits. So you have this path that's pinned down, like we talked about last time. It's completely pinned down. So we know what path is going to be. Moreover, every router along the path has a chance to say, I'm going to charge you so much for this quality of service. And so you can actually get end-to-end type of service in ATM. I got involved in ATM back in 1989. And I worked in it for about 7 or 8 years. But by 1997, it became clear that ATM was not going to work. ATM was not going to be able to compete with IP because of various political and technical reasons. And so all the work in ATM, basically, I had to get rid of. So 8 years of work, I just said, well, another terrible mistake, ATM. And that's the end of that. And it wasn't just me. It's hundreds of researchers, thousands of researchers, lots and lots of corporate dollars, research dollars, equipment, all sorts of stuff. Probably a few $100 billion worth of research and equipment and technology was basically thrown away because ATM lost to IP. And that's the tragedy behind the type of service field. So this doesn't actually work, and the competitor to this didn't actually win. So today, we still don't have quality of service on the internet. Today, we're kind of still stuck with the fact that your local router is going to put the Skype packets behind the BitTorrent packets, for example. You can't really prioritize it in any way, and we really don't have any kind of type of service. If it doesn't work, well, that's the internet. Sorry, we can't do anything better, right? So that's the problem we have, and there are some other issues as well. Okay, any questions about type of service?
So we don't have any type of service, or we have?
We don't. At this point in the internet today, the packets that are going to the internet, everybody is equally good or bad. Yes.
So if we know number 4 is kind of useless.
Yeah.
For version 6, do they also put that type of service in?
I think they don't. I'm trying to remember. I don't think they have it anymore.
Oh, okay.
So
yeah.
It says it's been depreciated with something called the differentiated services field.
Yeah. So differentiated services field is another half-hearted attempt to give you better quality of the differential services. There are two. It's called in-serve and diff-serve. So diff-serve, differential services, basically says that I'm going to give this packet better service than somebody else, but I won't tell you how good it is. It's just better than somebody else, right? It's like saying you're going first class. First class is terrible, but it's better than second class. Okay, so the snacks are better in first class than second class. So that's differentiated service, but the snacks are terrible in both classes, so it doesn't really matter. So that's diff-serve. So that even that doesn't quite work. Okay, I mean even that hasn't really made it. So it's a series of failures, and in fact one of the biggest failures in networking research has been how many papers have been written on this, how many books have been written. I wrote a book about it in 1997, and that's also unfortunately obsolete. So that's why I wrote a new one. Okay, we'll take a break, and then I'll come back to the rest of the fields. Okay. Next field is the length field. And now this is the length of the header plus data. And this is in bytes. And this is a 16-bit field. This is one thing that's important. So the largest number of bytes you can send is 65,536. This is a number that every computer scientist has engraved, tattooed on their brain, 65536 to the power 16. So that's the largest number of bytes. So the largest IP packet is 65536. Okay, so that's because, of course, the packets are variable length. All right, so now we come to 3 fields. Okay, I'm going to do, let me talk about a fun field, which is the TTL field, which stands for time to live. And the time to live field is like a countdown timer. It's like a bomb that goes off, and the time to live goes to 0. Packet is destroyed. Okay, so it's a field that's set to some number between 0 and 255 at the source by the source, and then it's decremented by every router. And then if field is 0, then you're going to drop it. That's what I mean by it's like a bomb going off. So first question is, okay, first question is why do it? Why should you why should there be a time to live field in the header? So why would you need it? Yeah, Andrew.
If a packet got really, really lost,
yeah.
After a certain amount of time, it would just drop it because you can assume that it would be resent.
Right. So the early internet had routing tables that were not particularly good, right? They would have what's called infinite loops. So you send it out. It's like going down. If you go down Ira Needles, that road over there, the boulevard, you have the traffic roundabouts. So imagine you go down this road, you get to the traffic roundabout, and then you go round and round and round and round and round forever, right? Until you run out of gas, basically. That's what happened routinely on the internet. It was very buggy in the early days, extremely, extremely buggy. So they said, okay, right, we don't want to have packets build up forever and take up bandwidth just going round and round doing no work. We'll put this TTL field. It was basically a hack. okay, because the routing tables weren't very good. Okay, well, routing algorithms weren't very good. And so that's what happened. It's a time to live field. Today, we still do it because we still have routing problems. Even today, there are routing loops, there are forwarding loops, and so on. And so a time to live is a good engineering solution. It says, look, yeah, our routing tables are supposed to be consistent. We are supposed to have everything kind of work. But if it doesn't, we're still OK. And that's what engineers do, right? You have the belt and suspenders. Your pants never fall down. Your belt and suspenders. So you have routing tables that are consistent, hopefully, and you have time to live field. And this is what we have today, right? And from a control theoretic perspective, which I won't go into later, I won't talk about that, but just for those of you who are familiar with control theory, has anybody here familiar with control theory at all? Ah, okay, then forget it. Okay. So if this field goes to 0, one other thing happens. What happens is that the source is sent an error message. And the error message is called an ICMP message. And that message is called, it's a special protocol. It's not IP, it's called ICMP Internet. I'll just spell it out. Or Internet Control Message Protocol. It's a special message. And this is almost the only place you'll see it, which is called ICMP. And it says basically packet expired or something like that. Okay, so you send your packet, and what happens is that if it expires, you get a message back, an ICMP message saying your packet just died, sorry. And from the source of the ICMP message, you know the IP address of the router where it expired, right? So this is how traceroute works. So the way traceroute works is like this. How do you find the path? So let's say this is the source, and this is the first router, the second router, this is the third router, and so on. So you all use traceroute for assignment 1, so you know what I'm talking about. What you do is this. You send a message like this, IP packet like this, and you artificially set the TTL to 1. What will happen is the first router is going to decrement it to 0, and it's going to send you back an ICMP message saying ICMP, okay, and then you have the source address, source equals R1. So you say, aha, the first packet along, the first router on my path to wherever is R1. Then what you do is you send the TTL equals 2, this is TTL equal 2, and this is going to come over here. This one is going to expire. You get back ICMP message, ICMP, source equals R2, and you can actually time it. You can say, I sent it at this time, and I got it back at this time, so that means that's the round trip time. So when you send a traceroute, you get 3. In the default parameters, you get 3 messages. What's happening is you're sending 3 packets with TTL1, 3 packets with TTL2, 3 packets with TTL3, etc., up to some maximum, and you just measure how long it took for each of them to come back. Okay. Now it's possible that the route changes. So R1 goes to R2, and then sometimes R1 goes to R3. Okay. In which case your responses will be R1, R2, and then the second time around will be R1, R3, okay, and you'll see R1, R2, R1, R3, and that tells you the routing table just changed underneath you, okay, so routing has changed. And you'll actually see that sometimes, especially on long paths, okay, when you did the Baidu path, you'd find often there were alternate paths or there were going to be routing changes underneath you, so even on the same time to live value, you'll get multiple IP addresses back, yeah?
So the value is 0 to 255, is that the number of nodes it passes?
Number of hops, the longest path that you can have, yeah. So so
it's not really quantified in time.
No, it's completely. It's decremented by 1 every router. Sorry. Decremented by 1 by every router. It's not time. It's number of hops. It's a hop count. Yeah. Any question about how this works? So now you know how traceroute works. Okay. Yeah.
What's the average time to live?
What's the average hop count?
Yeah. That a packet would have.
So we can't talk about average because it depends on where you're communicating with. So if you communicate to everybody inside University of Waterloo, your hop counts are going to be like 3 or 4. if you communicate mostly with international destinations. So the typical diameter of the internet, okay, the number I've heard is about 20. Okay, if it's above 20, chances are pretty good something is wrong. Some routing loop is there, right? But the longest paths I've seen is about 30, okay, and I've never seen anything longer than 30. But again, you saw Baidu was what, 32, right? That was fairly long. So that would be almost the longest you're going to get. You're going to the other end of the world, right? Yeah. Yes?
Suppose it drops before it reaches any
Destination. Yeah, so you'll keep getting these ICMP and you'll know, oops, my TTL is too low for the packet and you need to send it something higher. Typically, your operating system will set the TTL to be like 64 or 255 when you send it out. And
I mean, in the middle, like, so one guy will decrement it and send it to another guy, but that other guy never receives it, so who sends the SCM?
if it doesn't get that, if this packet gets lost, then it's got lost. I mean, you just get a star saying, I never got it back. I don't know what happened to it. It disappeared. Yeah. Yes?
For assignment 1, I got the star message
Yeah.
from some of the hops, but
Yeah.
then it started again.
Yes, yes. What it is that this router may be lazy. So it decremented it to 0, but it said, I'm not going to send you an ICMP. Sue me, you know, what are you going to do about it? Because they don't want to, right? There's no internet police going and saying, you must do this. No, I won't. Okay. And so they don't. So eventually you get to somebody who's nice. Yeah. Yeah. That's the problem with the internet as well, right? There's no internet police. Okay. Anything else? Okay. So that tells you what the time to live field is. So it's a good thing to have, and it's a useful thing to have as well because you can trace the routes this way. And traceroute was invented, about 20 years ago, and it's still one of the most useful tools we use for diagnosing what's going on in the network. It's kind of interesting. It's still around. Okay. Well, except what we have today, one of the tools I pointed to was traceroute with geocoding. So you kind of see how the packet is going, which is kind of cool. Okay. I'm going to erase this so I can continue with the fields over here. Okay, so the next field is the upper layer, or I think it's called the proto field, protocol. And to explain this, let me just draw a figure over here. If you remember the sort of the standard canonical figure, so let's say that the TCP sends a packet from this source to this destination through some number of intermediate hops shown by the dashed line. So the path is going to look something like this, right? Okay, and then into some socket above that. What has to happen at this IP? So this packet is going like so. This IP over here needs to know that it's not going to UDP, it's got to be going to TCP, right? Don't give it to UDP because UDP has no clue what these header fields mean, right? So we need to have something in the header that tells us what to do. And that's what's called the protocol field. It's a small integer. It's I think 4 bits. 16. One of the 16 options says this is the protocol that you should give it to once you're done processing. So it could be TCP or UDP. It could be ICMP and so on. So ICMP is sitting actually at the same level over here. It's a control message protocol. And so those are fields that are being used, okay? So that tells you where to go, and that's the protocol field. Pretty straightforward. Okay, now the 3 more fields which go together, I'll write them all at the same time because they are 8, 9, and 10. And it's the ID, the fragment offset, and the fragment flags. And there are just 2 flags, DF and MF. And this is don't fragment. And this is more fragments. Okay, so the reason, so these three fields are together for a reason, and what it is that it allows an IP packet to be chopped up into pieces and then put back together again, right? So let's look at an example over here. Let's say that we have some source over here, and that source is sending a very large IP packet. So here's your header, and that's the packet sitting over there. And so along some intermediate path, we come to a router, let's say R3, where this comes in, but it has to go on a link, and this link is only allowing small packets, only allowing packets of size, let's say 1,000 bytes. So this could be 64,000 bytes, and only 1,000 bytes are allowed on that link. So what do you do? Okay, so what you do is that you chop it up into pieces, and you put a header on each one of them, and this is what you do. So here, let's just take a simple example. Let's just take, this is 2,000 bytes. And the largest thing allowed over here is approximately 1,000 bytes. Okay, so what we'll do over here is that we'll break it up into two pieces. Okay, this is the first header, and another piece over here. So another header, and this is going to be 1,000. And it's actually not 1,000. It's 1,000 minus 20 because this is 20. So this is going to be 1,000 minus 20, 1,000 minus 20. Okay. And then this one is basically, let's make our life simple. This is whatever, 2,000 minus 40. So I'm just fudging the numbers to make it work. Okay. So this is a large packet, 2,000 minus 40, and it's split it up into two packets of 980 bytes each. What I want to do is to chop it up in a way so that the destination, which gets two packets instead of one, can still put them back together again. Right? And the way we do that is that in this field over here, we have the ID. Let's say the ID equals 2341. Then these both will have the same ID. ID equals 2341. ID equals 2341. That's the ID. Plus, that's the ID field. So they both have the same ID. So we know the fragments from the same packet. The second thing is that we have the fragment offset field. Okay, the fragment offset field over here is going to be 0. Offset equals 0 because it's the beginning of the packet. This one is an offset equals 980 because it says, yeah, I'm starting with the 980th byte, okay, or 981st depending on your convention, and that's the offset. And then the MF says that this is more fragments or not. So the MF over here is 0. Sorry, MF equals 1. This means there's more fragments coming, and here MF equals 0. No more fragments are coming, okay? And then, of course, we have the overall length. They both have the full length over here, and the length field for both of them, okay, is going to be, this one is going to be length of this bit over here, which is going to be 1,000, and this one is going to be length 1,000. Okay, but that's not part of the, okay, because each fragment itself is an IP packet, so the length field refers to that IP packet, okay? And so when the receiver gets this, what it says, it gets the first packet, it says, okay, there's an MF flag on it, okay, I've got to have more fragments are coming, and I'm going to put it into some kind of data structure which is indexed by 2341, saying, okay, I'm going to put it there, I'll wait. When the next one comes in, it says, okay, the offset is here, and the MF is 0, so it keeps waiting until it sees an MF equals 0, and then it knows it's got everything, right? At that point, you've got the whole packet, yeah?
What happens if one fragment is lost?
Right, so if a fragment is lost, eventually you're going to time out and throw it all away. Okay?
So you ask for the entire 65,000 bytes again?
Yeah, pretty much, it gets lost.
If it's lost, then is it R3's responsibility to reach?
No, the source. The source is going to retransmit. IP is best effort, so TCP's got the work of retransmitting it. If it's UDP, it never gets retransmitted. Right? Yes?
What's the minus 40, minus 20?
Oh, remember I said the link can carry at most 1,000 bytes. So a packet of 1,000 bytes, 20 bytes are going to be used up for the header, and the remaining 980 are going to be used for the data. Okay, that's why I was putting that in. Yeah. Yes?
So for more than two fragments, like the MF, like everyone in between is going to have MF equals 1, right?
Correct, yeah, except for the last one. That's right. The last one's got MF equals 0 because there are no more fragments. Yeah.
So all of that last part, that's the destinations.
The destination is going to, yeah, the intermediate packet routers are going to chop it up like this, maybe chopped up many times, but they never reassembled until the end.
Right. So
Right.
like the intermediate routers just see them as individual.
That's correct. Yeah, from their perspective, it's just there's just a packet with a smaller length, and then they just they just deal with it as they normally would. There's nothing extra. Yeah.
I assume ID is just like randomly generated.
ID is randomly generated, and what you want to make sure is that the ID isn't repeated for all the packets you have outstanding. So typically, you kind of choose them cyclically through the space, and when you come back to the beginning again, all the packets have died because the TTL has expired. Yeah, so we don't want to have any overlaps. This, by the way, opens up a big door for attack. Okay, and the door for attack, which actually is a homework question, but I'll give you the answer, is that if you send large packets and never set the MF equals 0, okay, what's going to happen is that they're going to be assembled over there, waiting in the reassembly buffer, and they're going to sit there and sit there and sit there. So I can take a server, and I can just fill it up with packets and never send MF equals 0, and they're going to keep waiting. And so all of the memory is going to be used up with these junk packets. So I can spoof the source, so they don't know who I am, and I send this bunch of packets, and it fills up the server's buffer. Okay, so I was teaching this class in 1996, and I discovered this attack while I was teaching in class, saying, oh, shoot, that's going to be a problem. And so anyway, I contacted the appropriate people, and so now it's protected. They don't keep it very long. They have a way to drain the buffers so that if you try to attack in this way, it will be taken care of. But it was sort of something I discovered by accident in teaching it. So yeah.
So is there a way to differentiate the fragments? So seemingly they have the same ID. So suppose
They're the same ID, but the offsets are different. The offsets tells you how far into the packet they are.
Oh, okay.
Yeah. Yes?
So how do they end up combining?
The combining, well, it's very simple, right? I have the ID, and I have these bytes. I know the offsets. So I just basically stick it in the right positions in an array of bytes at the right offsets. And when it's all done, I have the whole packet. Yeah. Yes?
So even for a packet that has not been divided,
Right.
they also have this A910.
That's right. All packets have these fields, even if they're not being divided, correct. So if you're not fragmented, your ID is going to be, each packet will have a different ID in it, correct. Each
Offset is 0.
0.
Then it's DF, right?
Yeah, and so I'll come to DF in a minute. So DF says don't fragment, okay? I really want it to be together. And if you do this and the router sees the DF flag, it'll drop the packet and send you a message saying, I had to fragment it, but you didn't let me, so I'm going to drop it. And so you get an ICMP message back saying, fragmentation necessary or something like that. And so that's almost never set. DF is a very rare thing. Okay, any other questions about it? Okay, so again, you can see the foresight of the IP designers in that they thought about the future that links maybe not be able to carry sufficient amount of bytes, so they put it into the protocol right up front, which is why, again, IP has been surviving for so long with very little change because they were pretty smart when they designed it. Okay. So incidentally, when I say they, most of IP was designed by two people, Vint Cerf and Bob Kahn. And Vint Cerf is the chief internet evangelist for Google. He's been at Google for the last 3 or 4 years. In fact, he came and gave a talk at Waterloo about 3 or 4 years ago. And Bob Kahn was working at the Defense Department at the time and funded this. But when he did this work, I think both Cerf and Kahn were at Stanford. So this is where this work was done in 1973. OK, so we have the version, header, type of service, length, ID flags, the TTL, the upper layer. So then we only have one more field, which is the important field, which is the header checksum. Okay. And the header checksum is basically a field that tells you so how many people know what a checksum is? Okay, checksum. Okay. So a checksum is additional piece of information that tells you whether you have a problem with if data has got corrupted or not. Okay. So the easiest example of a checksum is what's called a parity bit. So let's look at a parity bit for a moment. So parity bit is a bit added to 7 bits typically, the 8th bit, so that the number of bits in the string is either even or odd. So let's look at the even parity. Even parity. So let's say I have a string 10111011, and then I have this bit to fill in like so. And I want to make the number of ones even. So right now I have 1, 2, 3, 4, 5. It's an odd number, so I'll put a 1 over here, and that makes it even. Let's say I have a string like 0, 1, 1, 1, 1, 0, 0. Then I have another bit over here. So this I have 1, 2, 3, 4 bits, which are even. So I'll put a 0 here because I don't need another one. I've already got even number of bits. So this bit in a box over here is extra information. It's redundant information. It's not something that carries any content at all. However, it allows us to detect that something went wrong. So if one bit flips over here, let's say that flips to a 0, then it doesn't have an even number of bits. So you say, oops, made a mistake. You don't know which bit flipped, but you know some bit flipped. And of course, 2 bits might flip. Okay? If 2 bits flip, then you're out of luck. So you're going to say, okay, probability of 2 bits flipping is very low, so ignore it. And, but 1 bit flip you can detect. So this is an example of a checked bit. Okay, so checked bit. And this is typically used in memory. So if you buy RAMs, they'll say, you know, single error detect. Anyway, so single error detect would be this would be a single error detect parity bit. Okay, and you can do the same thing with odd parity. And a checksum is similar to this. And essentially, you can think of some set of numbers, let's say A, B, C, and you add them up to get something. And you add extra D so that the sum always adds up to some number like 65536. Okay, because that's all ones, right? So that would be an example. So you want to send A, B, and C, and you add the extra D, whatever D is, so that it adds up to this. That's called a checksum. Okay, and if any of these numbers changes, they won't add up to 65536, and then you know something happened. That's almost exactly what's done in the header. So we take all the fields, we treat them as numbers, and we add them all up. And at the end, we add whatever bits are required so that the whole thing adds up to some number. Okay. Like that. Yes?
Just to clarify, that D changes all the time.
Yeah, D is, so if A, B, or C changes, then D changes. But D is chosen,
Make it always add up to
that's
that.
right, yeah, chosen so that sum equals 65536. That's a check sum. It's a sum. Okay. So this way, if anything happens in the IP header, something gets messed up, you know that the header checksum is probably not going to work out, in which case you drop the packet. Now, it's not guaranteed. It could be the case that something is messed up in just the right way so that it's not detected, but at least you have some hope of doing it. If you don't do it, you're out of luck. Okay. Now, so anyway, so one could argue, why do these bits get flipped? It happens all the time. It happens because of lightning. Somebody turns on an electrical drill, causes electromagnetic spikes. It happens, if you have optical fiber and it got bent by a little bit more than required, you have that happen. Many, many things can cause bits to get corrupted, and it's always a good idea to try and put a checksum in. Okay, yes?
How do you know what the sum is? Is it always 655?
Because this is the internet checksum. It's defined to be the sum should be this.
Okay.
Right, so it's defined that way. But there are many other ways of doing error detection and correction. In fact, there's a whole theory behind error correction, which I won't go into. It's a sub-branch of information theory, but I won't get into that. Yeah. Yes?
So, for example, if a small packet,
yeah.
then if we want to check some,
yeah.
so maybe like 40% of the message is useless.
Remember, we're not checksumming the data, just the header. We're just checking the fields in the header. This field, the TTL field, the protocol field, the length field, options field. These fields, yeah, just those fields. It's on the header. It's a header checksum, not the data check. TCP has the data checksum. TCP says I'm checking all the data, but IP does not. IP only does the header. Yes?
I'm confused about what the ABC is.
I'm just saying that, let's say, this example of what a header checksum is. Let me maybe do an example over here. Let's say I define a checksum, okay? I define it. This is not what the internet sum is doing. Let's say checksum, okay, defined to be sum equals 100. Let's just do a simple example like this. Okay, I want to send you 3 numbers, 3, 10, and 20, right? And then I can fill in this number so the sum is 100. Okay, so this is 33, so I put 67 in, and it sums to 100. Okay, so if I get these 4 digits, 3, 10, 20, 67, I'll say, yeah, that's good. Okay. But if this gets corrupted to 21, for example, then it won't add up to 100, then I know some problem happened. I don't know what it is exactly, right? That's,
So
yeah.
the D is chosen like right when it's sent.
That's right, yeah. You process process all the fields. When you're all done, you say, okay, the last little bit, okay, I'm going to put it in. That's a checksum. Okay. So do you get what's going on? This is what's done for your Visa card numbers, by the way. When you go to an internet check website and you put in your Visa card string, the 16-digit string, it's sometimes an invalid number because it's a checksum and set. There's an algorithm that says, yeah, these numbers don't make sense. This doesn't add up to something. Okay, and then that allows you to detect that it's not a valid number. Okay, so that's the checksum. And then the last two bits, and we'll take a break after this, the last two fields are source address. I already talked about this. Obviously, we need source, the destination address, and then that's it. We're done. That's all the fields there are in the IP header. Okay. So these are actually the most important fields, but since we already talked about them, I'm not going to spend any more time on that. Yes, Tommy.
So Andy said the destination is optional, right?
The destination.
The source, sorry.
The source is optional. It's optional in the sense that if you don't want to reply back, yeah. But if you do anti-spoofing, you know, which all of you did the homework assignment. Oh, I forgot to bring it in. Yeah. Okay. Yeah, you see, most routers today do anti-spoofing. So they look at they make sure that you know, you're not going to use a random address. If they can't serve you, you can't send it to them. It's the way that works. And so then it's not optional anymore. But technically speaking, it is optional. Yeah. Any other questions about the IP header? So as you can see, you get like an X-ray into the whole protocol just looking at these fields one by one. And this is true for any protocol. Yeah.
When you're, wait, does this have anything to do with like blocking cookies, and then people won't let you block cookies? Some sites, like Google won't let you access their site unless you.
That's got nothing to do with the IP though.
Oh, okay.
Yeah, IP cookies are at the
source address.
oh, I see what you mean. Cookies are at the HTTP protocol level, and this is at the IP kind of way below.
Right, so they're just
Yeah, no, it's not relevant here. Yeah. So we have the IP header. So let's go into the address allocation part, which is, I don't think we're going to get to this today, but anyway, we'll get to address allocation. So I want to solve the following problem. I have a laptop or a desktop at home or at work, something like that, and I need to get it an IP address. Okay. How do I get the IP address? How do I get this number which is going to be given? Now, I'm not talking about the theory of IP addresses, which we now believe, we understand. The theory says we need to have geographical locality, we need to have network number and subnet number, all that good stuff. But no, I want to go with the practical part of how do you actually get it in there. And most of you are familiar with this, so I won't spend too much time on it. I'll just hopefully put that in context of what we're doing today. The first thing we need to understand is the IP address, okay, even though we talk about it, okay, is for an interface, not a host. Okay. So if you have two interfaces, you'll have two IP addresses. Okay, so many of you have laptops which have a wired interface and a wireless interface, in which case you'll have two IP addresses, one corresponding to each interface. Okay. A router, by definition, must have at least two IP addresses, right? You're going to have two IP addresses because you're going to route, you're going to pick up from one interface and send to some other interface. You've got to have at least two, which also means that any device with two interfaces can be a router. Okay, so your laptop, if it's connected to the Wi-Fi and to the wired network, can actually serve as a router. It's just a bit of software inside and it allows you to become a router. So we can't really distinguish between routers and end systems anymore because anything can become a router. So to be more specific, let's say you have a smartphone which has connectivity on 3G, okay, and also has Wi-Fi on it. You can certainly make it into a hotspot. So Android phones allow you to do that. We just say, okay, this device which used to be like an endpoint now has become a router because I just turned on the software, okay. And so that's certainly possible, and certainly IP allows you to do that because an address is for an interface. Okay. Right, that's the first thing. Okay, so how do we get it there? So how do you decide what IP address you get? And there's sort of two steps involved in it. Okay, the two steps to get an address. Okay, the first one is allocation. And the allocation means that some global authority has to allocate you the IP address, because everybody shares in the same 32-bit space. So somebody who has global reach has got to say, okay, you can get it. But typically, when they say you, it doesn't mean you as an individual. What happens is the allocation is almost always to organizations, because it's too hard otherwise. Okay, and the organizations will get an address block, get a block. And we know what a block means. It's like a /20 or a /25 or a /32, whatever. That's not a /32, I'm sorry, but a /16. They get a block of addresses. Okay, and once they get the block, then they allocate that out to all the people in that organization, right? So the organization could be your ISP. So if you have service from Rogers, for example, Rogers has gone and got a block, and then they allocate it to their customers. We'll see in a minute how that's done. But how does Rogers get the allocation in the first place? The way that works is that we have something called the Internet Assigned Numbers Authority. And it's often called IANA. That's the acronym for it. So IANA is the entity which is a sort of a quasi-governmental or quasi-international organization, and it's based in the US, which because that's where it started out from. And they have responsibility for and they have control over the entire address space of the internet, all 32 bits, they control all of it. And what they do is they basically divide it up into, I think, 5 or 6 registries. I can't remember, that's either 5 or 6, which are we call registrars. And the one that's relevant for us is ARIN, which is the address, American Registry of Internet Numbers. Okay, so American Registry of Internet Numbers is the one that's responsible for North America, Mexico, the Caribbean, and so on. And then there's one for Latin America, there's one for Japan, there's one for Europe, and then there's one for Asia, Middle East, something like that. So I can't remember all of them exactly, but the one that's relevant, so RIPE is Europe, for example, and so on. ARIN gets a chunk of addresses from IANA. So IANA says this is the entire space, and they say, okay, ARIN, you get this chunk. This is the American Registry of Internet Numbers. And so if Waterloo wants IP addresses, it goes to ARIN and writes an application, says, can we please have, a /16, okay? And ARIN will say, all right, fine, Waterloo, you look okay. And they give you the chunk. And then Waterloo, in turn, takes the chunk, a /16, and breaks it up into typically subnets, which are /8s, /24s. It's 256 byte chunks, and they give subnets off to different departments and so on and so forth. So we get an allocation, and that allocation is managed internally. Okay. Same thing is true for Rogers. Rogers goes to ARIN, makes a case, gets some IP addresses, and so on. And so from the perspective of IANA, they just basically hand off chunks to these regional registrars. The regional registrars then follow whatever process they want to allocate chunks to the organizations inside them, and so on. And when we do whois, right, or we use in the assignment one, you saw what chunk Waterloo had. So whois database keeps track of all these allocations, okay? And so there is some kind of authority to keep track of this. Interestingly, these things are basically free. There's nobody charging for it. Okay, it's like the address space. You don't have to pay money for it, but it is certainly very difficult to get you to make a very strong case for it. I should add a couple of sort of historical footnotes since I have a bit of time. I want to quickly tell you 2 things just to tell you how this kind of works. The first one is in the early days, the chunks were handed out pretty arbitrarily. People would get /8s, which means 2 to the power 24 addresses, and they would just give it out because they thought internet is a lab experiment. Who needs it? So when I was a long time ago, I used to be a researcher at Bell Labs, and in 1995, I was working at Bell Labs, and internet at that time was not very commercial. In fact, it had just begun to be commercial. There was almost no commercial activity. And AT&T, which was owned Bell Labs at the time, was were kind of interested in using the addresses, and they went to Aaron and said, hey, can we have some addresses? And they said, oh, you already have something. It turned out that lying in the back pocket of AT&T, which they didn't even know was a complete 12, they had a /8, it was 12 dot star. It was a /8 address, 2 to the 24 addresses. They didn't even know they had it. It was allocated to Bell Labs in around 1975, and nobody bothered using it because we were using something else. We were using a /16. And this was worth, several $1 billion worth of revenue to AT&T. It was just lying around, and they didn't even know they had it. Okay, and because in 1995 nobody really cared about it. It was like, yeah, whatever, Anyway, the other story is that I remember when India got internet, it was in 1989, and all of India was allocated 255 addresses. The Indian population at the time was not very high. It was only 900 million people. It's now 1.2 billion, but all 900 million people got 255 addresses. So that should be good enough for you. Okay. And of course, at that time in India, in 1989, there were only 6 IP addresses that were being used, so it was 255. So it was not such. There are exactly 6 end hosts in India at the time. So I could tell you more stories about it, but I won't. Yeah, so I don't know about China, but I knew the situation in India at that time. So there's a lot of, let's say, regional disparities in the numbers allocation, and there's a lot of fights going on about who should have more addresses and so on and so forth. The people generally agree on at least 2 things. First, we're pretty much running out of addresses, and I'll talk about that, how to deal with that in a moment. And second, some kind of governmental or multinational oversight needs to be happening, because IANA is actually a bunch of ex-hippies sitting in an office in Santa Monica in California deciding what to do, because they used to be hippies and they never grew out of it, and they're still around handing out addresses, and people think the UN should be involved and so on, but it's not clear what's going to actually happen. Yes?
How do they even keep this organization running if you're not charging?
It charges a small amount, considering this worth billions of dollars, they charge you a couple of million, it's not a big deal.
Oh.
It's not much. It's not much compared to what it's actually worth.
Oh.
Yeah. It's a small amount. I think they charge you like $500 in allocation or something. I don't know what the exact number is. Yeah.
Can they retrieve addresses?
Yeah, so they encourage you to return it. And what they need to do is that each organization needs to justify that their allocation is being used. So you need to say what percentage is being used. And if the percentage is being used is not high enough, they'll actually subclass you. So you have a 20/16, let's say, and you're not using it, they'll give you /20, and they'll take back the addresses and they have to renumber.
And they do that like every use?
They don't have any police, they have no way to enforce it. So it's all done on trust, basically.
Oh.
And at the top level, you can enforce it by changing the routing tables and so on. But yeah, it's as I said, it's a lab experiment, right? It was a lab experiment, and it just, we don't know. There's no particular rules about it. Yeah, it's the same thing with domain names, right? I mean, we know all the problems with that. So okay. So we got that part done. So how do we now? So now we know how the organization got the address, the allocation part. The second step is to actually hand it out. And the typical way to hand it out is is basically using DHCP. So how many of you know what DHCP is? Actually, I should turn around. How many of you don't know what DHCP is? Okay, so DHCP is Dynamic Host Configuration Protocol. So Dynamic Host Config Protocol. And let me explain how that works. It's actually really, really simple, and it's okay. So you remember my assumption that you can get to any address in the LAN, right? Remember that assumption? So I'm going to have some kind of local area network, or I should say, I can get any address in the subnet. So here's my subnet, and so anybody can get to any address in the subnet. And I'm going to have a special address over here. And it's called the broadcast address. And the broadcast address is typically basically the subnet number followed by all ones, however many it takes to fill it out. So if I have a whatever slash something, if I fill it out with all ones after that, that's a broadcast address. That means, okay, broadcasted. And we also have we have another way of doing broadcast inside the subnet, which is called a link layer broadcast, but let's ignore that. I'm just going to assume that there is a special address I can put on my packet, and if I put that in, everybody in my subnet can hear it, okay? That's all I want to know. So that's all the assumption I'm going to make. I'm going to send it out, everybody gets it, okay? So in this subnet, we'll have a server, which is called the DHCP server. And here is my laptop, let us say, which needs an IP address. So the laptop doesn't have an IP address, okay? So what the laptop is going to do is that it's going to send a broadcast out saying, I need an IP address, can somebody give me an IP address, okay? The DHCP server, because everybody can get to it, certainly the DHCP server can get it, and what it does is it says, okay, I have a pool of addresses, I have a pool of IPs, okay, and it's going to pick a pool of IP and send it back to the laptop saying, here, use this IP. And at that point, it has an IP address, okay? So that's basically it, okay? The couple of extra details. One detail is that when it gives the laptop the IP address, it gives it a lifetime. It says, okay, you can have this, but you have to give it up after a certain amount of time. It's called a lease time. So the lease says you have it for 1 day or 1 hour or whatever. At the end of the lease time, the laptop has to ask again, can I have an IP address again? And you do it. And this is what happens when you have dynamic addresses at home, right? When you have a DSL line or a cable modem line at home, your endpoint actually almost always gets a dynamic address. And so every time it expires, it goes ask for something, and it may get the same IP address, may get a different IP address, right? But the nice thing is if somebody isn't using it, then the address pool can be given to somebody else. So the total number of IPs that's allocated to, say, Rogers is smaller than the number of endpoints that are actually present because they don't all need it. That's one advantage of doing this. Okay, that's the first wrinkle. The second one is, well, if it didn't have an IP address, how did it get from here to here in the first place, right? And the way it works is that we have, at the subnet level, we have at the LAN or subnet, we have a different address, and we call that the media access address. And we'll talk more about that later when we talk about the link layer. And this stands for MAC, so it's MAC, is what we call it, a MAC address, a media access address, a MAC. And so the address that we use over here to do the broadcast and to get the reply back is the MAC address, okay? And we guarantee that everybody here can get to the MAC address. If you send out a source to be your source MAC address, which is your Ethernet address, I guess, then you're going to be able to get back to it using this. So to summarize, what happens is this: the laptop turns on, and it reads the interface and says, what's your MAC address? It says, okay, my MAC address is whatever it is. Once you have the MAC address, it sends a broadcast. It sends a broadcast on actually the subnet saying, I just woke up, I need an IP address, can somebody give it to me? The DHCP server gets this address and says, okay, here's somebody with this source MAC, and here's my pool. So it picks up one of the IPs from the pool, gives it a lease, and says, okay, and sends back on the source MAC, says, here's your IP address, and at that time you're configured. Now the other thing the DHCP does for you, in addition to source MAC, it actually gives you the IP. It also gives you the subnet mask, which you need, because you need to know which subnet you're part of, and I'll talk about that when we talk about routing in a LAN. It tells you who your DNS server is, and it also tells you who your router is. What's the router IP? So these are the 4 bits of information you get from DHCP, and you don't have to use DHCP. You can always do it by hand. Okay, if you know these values, you can certainly go into manual mode, type in the IP, the subnet mask, the DNS, and router IP. Once you have these 4 things, you're on the internet. Basically, you're done. Okay? Compare this with getting a cell phone. Right? When you go to a cell phone, you can't just go to Future Shop, buy a cell phone, and use the manual key and type in your IP, your subnet mask, DNS, and you're done. Right? No. You have to give them your credit card. You have to get a special IMEI number, and then you have to get that registered and all this other stuff. Why? Because it costs them real money. You're paying real money for the cell phone network, whereas here you're getting on the internet. So this simplicity makes it possible for the internet to grow like crazy, but also makes it possible for anybody to spoof anybody else because there's no validation. Anybody can just type in these things.